Good afternoon. Thank you for staying. I know it's it's a lot of content today, but so my name is Jean-Francois Bobier. I'm a partner and director at Boston Consulting Group. So we are strategy consultants. You might ask why we are doing quantum, but we truly believe that it's transformative, and we hope that our clients will also realize that. And we've been now researching quantum since 2018. We have about 15 publications, and we are definitely excited about quantum error correction. So yeah, I'm going to pass to you, Steve.
Great, yeah, thank you. Hi everyone, I'm Steve Brierley, CEO and founder of Riverlane. So at Riverlane we work exclusively on quantum error correction. So we don't develop qubits ourselves, but we work with companies that do. And so it's a great privilege to work with and see many of the great progress that's been made over the past 5 years at least. So we're based in Cambridge, Cambridge, UK, and Cambridge, Massachusetts. We combine chip design expertise with quantum error correction expertise, and that's because actually implementing error correction is essentially a real-time data processing problem, and so we need to be able to compute very quickly and keep up with the qubits. So that's really our job.
Hello everyone, I'm Yuval Boger. I guess in France it's Boger, right? It is what it is, and I'm Chief Marketing Officer of QuEra. QuEra makes neutral atom computers. We were a little bit in the news in the last couple of months because of results that were published by Harvard and QuEra with regards to logical qubits, and I'm very happy to be here.
Hi everyone, I'm Peronnin. I'm the CEO and co-founder of Alice & Bob. At Alice & Bob, we build universal fault-tolerant quantum computers out of superconducting qubits, but a special kind of superconducting qubits called cat qubits that are meant by design to correct for one of the two types of errors, namely bit flips. And this simplifies a lot the design of fault-tolerant quantum computers. The claim we make is that it would take 200 times fewer quantum bits thanks to this approach. So we're a hardware player fully dedicated to fault-tolerant quantum computing.
So okay, so let's get started on error correction. So maybe we could start with maybe we could start as a warm-up, like how do we define quantum error correction? Because there's a whole spectrum from detecting errors, right, mitigating them and suppressing them. Where are we today, and where do you believe we can get? Maybe Steve, you can start.
Yeah, sure. So I would say the key metrics to watch are qubit fidelities, and what you've seen over the past 2 decades are fidelities improving and improving to the point where we're getting close to or at what's called the error correction threshold. So error correction works by quantum error correction works very similar to classical error correction. Like you add additional qubits so that if any one of them fails, you can still recover, right? But if each of your individual qubits are so noisy, if you add extra qubits, then this just makes the system worse. So there's this threshold at which you need to be better than in terms of fidelities for error correction to even start to work. And I think the really exciting thing about the field is we are now really close to that threshold. And so there are a bunch of techniques that help improve qubit fidelities. So one of those is called error suppression. And so that includes things like dynamical decoupling and that kind of thing. So you're sort of trying to improve the individual qubits. So you definitely need to do that. Error correction is this extra layer you put on top, which is a kind of active process where you start measuring some of your qubits in order to read out some of that give you some clues about where the errors have occurred, and then you actively correct. So you're kind of pulling entropy out of the system. So that's kind of quantum error correction. And then there's this last thing called error mitigation, which is a kind of repeat your quantum algorithm some number of times and then try to do a bit of statistics to infer what you were supposed to get even in the presence of errors. So that tends to add a bit extra on top of any quantum computer. So these three things combine very well, and I think we will continue to see them being combined over the next 5-6 years.
And so Yuval, your computer has made some of the headlines about quantum error correction. in that spectrum that I was describing, where you think you are, and when you will be very in the future.
So ultimately, users need better qubits. They need better qubits because they want to run long calculations. And if you look at today's state of the art, say 99.9 fidelity, that sounds great, but it means that there's, on average, an error every 1,000 steps, and you cannot do anything, or you cannot do too many things that are useful with 1,000 steps. So all these techniques are designed to, okay, can I get it from 1 in 1,000 to 1 in 1,000,000 to 1 in 1,000,000,000, and so on and so on. And so we're at an early stage of that journey. As Steve mentioned, a lot of technologies have sort of improved the quality of the qubits to something that can benefit from error correction. And now we're entering the era of logical qubits, which are a collection of physical qubits, a little bit like a classical repetition code that are designed to detect and correct errors. As far as we're concerned, we'll have a machine this year with, we announced 10 logical qubits. I guess that's the minimum. We hope to have more. And that 10 logical qubits by itself is useless. You can run it on your phone. You can run 10 perfect qubits on your phone. But it's useful in getting to understand what error correction means and prepare for the future. In our roadmap, 30 logical qubits in 25, 100 logical qubits in 26, and somewhere between 25 and 26, it becomes really interesting.
Yeah, Theo, same question for you.
Yeah, maybe so at Alice and Bob at the moment we're on the same path, and we recently unveiled a 16-cat qubit device on which we're currently working to implement this repetition code. So in our case, we only have one type of error that we're left with to correct for, because we natively correct bit flips, and then we need to correct the remaining phase flip through redundancy. So this 16-cat qubit device called Helium-1 is a very simple code, a repetition code, so sort of a majority vote to correct for those phase flips. And we're currently exactly working on crossing the threshold of error correction. We're slightly above at the moment, slightly worse, and we need to get it below. And what I think is very exciting in the field overall is that we're really nearing this, what I like to call this Sputnik moment, the moment where man-made machines start to escape decoherence. And that's a very profound milestone, I think, in my personal opinion, for mankind. Just like Sputnik escaped gravity for some time and was just a signaling machine announcing the beginning of the space era, I think whatever the platform, as soon as we start having proper logical qubit that through time can escape decoherence, extend exponentially their lifetime and coherence time, that would be a very strong signal for the beginning of the quantum era.
So going back to that point, sorry, I will stay on you a little bit because you were making that point. But, so again, there are logical qubits and logical qubits in a way. For example, there's always a caveat like how many operations I can make, how long can I make the calculation. You know, how do you see that? Because again, it's one thing to start having that, but then there will be a lot of other conditions that will need to be met for it to be really useful.
Yeah, so I think one of the challenges we're facing as an industry is the lack of standard or common ground for language when it comes to logical qubits. Most of the metrics that are discussed today were meant for NISQ era in terms of quantum volumes, those kind of things. They're absolutely not well suited for fault tolerance. And indeed, well, depending on who you're listening to, the definition of a logical qubit might vary quite a lot in terms of the level of fidelity. And this is by design of the logical qubit, because we're on an exponential slope as soon as you're under the threshold. So you might be at the very beginning of that slope, and that's already amazing if you can show that you start to improve exponentially as you increase the distance. But if you want to run algorithm, let's say the target of 100 logical qubit is a very good target, but then you'll need depth of maybe 1 million gates to run your algorithm. So those are, I'd say, proper logical qubits. So indeed, I think we have to work as an industry to define a way to distinguish between those orders of magnitude when it comes to logical qubits.
So Yuval, can you tell us more about your roadmap? So when you mention 100 qubits and so on, so how do this translate also in terms of number of operations?
So there's, as Theo said, there's more than one type of logical qubit. There are a couple of ways to encode, and even in that Harvard paper, there are different code distances. There are codes that only detect errors. There are codes that can correct errors, and so on and so on. And by the way, even error detection by itself is useful, because imagine if you ran an algorithm and you have a way to say the calculation is wrong. Well, you can, at the very least, you can discard that result and run it again. So even detection is useful by itself. Theo was mentioning distance, and the code distance means how many errors can you correct. So code distance 3 means that you can detect and correct 1 error. Code distance 5 means 2, and so on and so on. And as you get to larger and larger code distances, there's a trade-off, because you use more physical qubits to create one logical qubit. So no free lunch, right? So the system that we are developing, one of its goals is to allow people to experiment with different types of encoding, with different types of qubits. And by the way, it also depends on the modality. So for qubits that have moving, the architectures that have moving qubits, you could do things that you cannot do in static qubits, like superconducting, because you can move the qubits around. You can make codes that are more efficient. And so I don't think there's an easy answer to your question. It's open for researchers to see what they can get out of the machine. They can certainly replicate the Harvard experiment and then take it to the next step.
I just going to ask another question on that, because I was very impressed by obviously your results, and it was amazing to see that at some point you need to inject atom back to continue to sustain the error correction. How far are you from being able to do that? Is it already on the 100 qubit device, or?
Oh, definitely. I mean, we are working on it. The fact that you can correct an error is good, but our goal is not to get a prize for error correction. Our goal is to be able to create sustained algorithms, and for that you need to correct and continue to the next step of the algorithm.
So you'll be able to do that. That's going to be interesting to see, because it seems difficult to do, right? Steve, you see a lot of qubit modalities from your standpoint. How do you see that landscape in error correction? So obviously, we have two front runners with neutral atoms and superconducting qubits. Alice and Bob did announcement. IBM also did announcements. How do you see that landscape from your perspective? And what are the pros and cons, basically, of the different modalities, if you can share with the group?
Yeah, I think it's actually 5 years ago, I think I would have said, hey, only one of these approaches is going to make it. There are 5, 6 different ways to build a qubit, and at that point I really felt like there's going to be some fundamental science barrier that stops most of these, and there'll be a heroic kind of breakthrough of one qubit type. But that's actually not what we've seen. We've seen progress right across the different qubit modalities, and from ion traps to superconducting and neutral atoms and silicon and photonic systems. And I think this is actually just really amazing. And I think the first error-corrected quantum computer. So I'm going to suggest a metric, which is the number of quantum operations, or QOPs. So the first million quantum operation quantum computer, or mega QOP system, will be the first that cannot be simulated on any classical computer. And so that's going to be a really exciting moment in, I think, the history of computing. And it seems like from today, it looks like all of the qubit modalities could get to that point, that there's no kind of fundamental science challenge to overcome to get there. And that's because it doesn't require millions of physical qubits, so it doesn't yet require things like networking, which we think is a very optimistic way of continuing to scale, but haven't yet been fully solved. So there are a bunch of kind of science problems that get kicked down the road a little bit, and so I'm very excited to see the whole field get to this point where we actually have multiple different qubit types capable of developing error correction. And of course, then we need to go to the next scale, right? So then there will be the gigaquop era and then the teraquop era. I think that's really what the users care about, like how much computation can I do before the quantum computer starts to fail. We tend not to worry about that in classical computing because our transistors are so good. But in quantum computing, it's the key thing. I think as the industry matures, we might start caring about teraquops per second, or we will start to care about speed. But right now, I think it just, can you get the computer to work at all is the big challenge.
So talking about that, I think there's what is nice that now that our correction is in front of us, a lot new number of KPIs that we didn't thought about are appearing. You mentioned clock speed, which is going to be an important one. For example, 1 hour on if you multiply it by 1,000, which is right now the ratio between, for example, trapperion and superconducting qubits in clock speed. So 1 hour becomes 42 days because 1,000 hours it's basically 42 days. So clock speed is going to be important. But I was wondering if there are overall metrics we should be aware of. So for example, we are aware that there are certain gates, if I think Clifford and Clifford gates that may come into consideration. Maybe connectivity might also come back as an important KPI. What are your view on the overall KPIs that people should look? So obviously, number of hops now will be like front and center, but are there other KPIs that people should look at?
Yes, so I think kind of from an algorithmic perspective, designing for an error-corrected quantum computer is different to designing for a NISQ quantum computer. So you really care about so the expensive gates are the T gates. So these are the magic gates, right? And so so you get a bunch of gates that are quite easy to implement, and then there's one gate that's hard. Right, there's in fact a very nice no free lunch theorem in error correction. So kind of designing for minimizing T gates in algorithms is going to be super important. I think there's a lot of interesting trade-offs. So although there are some slower clock speeds, actually you can often trade space and time in quantum computing. So it could well be that a slower system just needs to have more qubits. So there's a kind of bigger system that's operating more slowly. So kind of area, like space times time is really important. That's why I like this quantum operations metric. It's really the area of the circuit.
And again, that's why also some other metrics like connectivity could help because also you might lose time swapping operations, to get qubit closer. On some architecture, it's different. Actually, it's one of the areas also where neutral atoms have some advantage. The connectivity is slightly better, right? Can you take more about where you have good metrics that are useful?
I think when we say we're entering the era of logical qubits, it means we're exiting the era of physical qubits. So at some point, I think people will stop caring about how many physical qubits you have. Just like no one cares about how many transistors you have in your phone. You say, oh, I've got a phone, it's got this camera, it's got this display. The metrics are now different. So I think the key numbers are how many logical qubits do you have? How good are they? Then you have sort of second-tier metrics that might be important. So for instance, in the neutral atom architecture, we can do parallel gates. So we can do many operations, many identical operations on pairs of qubits at the same time. So if you write the algorithm correctly, or if the algorithm gets compiled correctly, then it becomes very efficient. So I think these can be secondary, but number of logical qubits, the error rate, and then speed or other things as well.
I saw you smiling when, and Theo, I know you care about T-gates a lot because we already had discussions about that. Can you tell more about how much care you put into actually implementing the entire suite of gates and in your architecture?
Yeah, maybe first I also like to advertise some of the very good aspect of neutral atom there when you're talking about parallel gates. something that is striking is how you manage to multiplex control and thus reduce the cost of the control stack. And when you talk about metrics, I think at the end of the day, what the customer will care about is how much does it cost to run the job, which relates to speed, complexity, a lot of things, but it's kind of the overall overarching metric. So in our case, we indeed do not have the capabilities of moving qubits around, but here I'd like to make a small technical note in differentiating the connectivity at the physical level from that at the logical level. So the connectivity at the physical level is really how wired your quantum computer is. And this will impact a lot the type of code you can do. And what is amazing in QuEra's and MIT's paper is because of the flexibility of the you have of moving atoms around, you can basically run any types of error correcting code, which makes it a perfect platform to try out errors. And I guess it's the favorite toy for Steve's team to play with. In our case, it's slightly different, where connectivity has a cost, and what was very exciting with our latest result, the LDPC plus CAT architecture, is that we managed to implement some very efficient error correcting code with only local connectivity, where IBM requires long range. So that's at the physical level. It dictates the type of code you can run. But then once you're doing error correction, then you have a magic tool in your toolbox, which is lattice surgery. It's basically you can extend logical qubits and have them play snake around in some sense to go and touch other logical qubits, which virtually provides you with an all-to-all connectivity at the logical level. That being said, you have this no-go theorem preventing you from doing some type of gate, so it depends on your code, but often it's T-gates or Toffoli. I mean, it's a non-Clifford gates. And here, well, you need to do other tricks like magic state distillation and those kind of things to be able to run that. So for us, it's really a list of boxes to tick. So first being, achieving the logical qubit, being on the threshold, better than break-even, then be able to do lattice surgery, so split and merge, extending your logical qubits, then being able to do Clifford gates, so the easy one at the logical level and checking that everything still works very well, and then the tough part, which are non-Clifford gates. And here we hope to demonstrate all the key ingredients on our 40 CAD qubit device within the next 2 to 3 years. But that's our internal target. We still have a lot of work to do to get there.
Okay, going into timeline. So Yuval, you shared a timeline on error correction. Can you maybe remind the audience what is basically your timeline, and maybe, I don't know, maybe you cannot share beyond that, but what are the prospects after that timeline you could to share with the audience?
So our commitment is to make 10 logical qubits in 2024, 30 logical qubits in 2025, and at least 100 logical qubits in 2026. Year by year, we're adding additional things like non-Clifford gates, multi-step operations, and so on. It's all built on the fundamental architecture of a storage area with long coherence time, and entanglement area, excuse me, that allows for parallel operations, a measurement area that allows to extract the syndromes, and so on. In our architecture, we do not need lattice surgery because we can basically take these logical qubits, these patches of qubits, and sort of move them one on top of the other, and then move them back. And so on.
Nice video, by the way, for those who didn't see them.
Yeah. So after 10, 30, 100, that's it, right? 101, 102. No, of course, we'll continue to improve that. We'll continue to get, I mean, even the physical qubits get better. And so we published the 3-year roadmap, and I think that's enough work for us at the moment.
You know, okay. Steve, what's your view of timing, the sequence of error correction based on your vantage point? Can you tell what are your predictions or your observations? can we see large commercial systems before 2030, for example? That would be nice. Yeah.
Yes, yeah, very much so. I mean, and the UK government has as its mission to build the first mega quantum computer in 2028. So, yeah, I think in the next 3 to 4 years, whether it's a QuEra system or a Alice and Bob system, I'm very optimistic that there will be the first error-corrected quantum computer. And I guess our job is to build the control system, build the error correction fabric that does the classical processing. So, kind of coming out of the system is the error data, and that all needs to be processed, and the syndrome data needs to be moved around different decoders, kind of, and actually implementing logic. So, kind of taking the syndrome data and delivering the logic as a classical problem. That's in itself a big challenge, and so that's what we're focused on. And our roadmap lines up with the most ambitious roadmaps of the companies building the qubits.
Can you tell us more about? I guess there are some environments where it's really difficult. For example, when there is cryogeny involved, so you need not to move stuff around. So you probably need to compute as close as a QPU as possible. How hard it is for you to achieve that?
Yeah, that's an interesting question. So currently systems have cryogenic qubits and room temperature control electronics. Yeah. And one of the challenges that creates is that you effectively need to send microwave signals into the fridge. And so that requires a lot of cabling, wiring, basically, and that's expensive and challenging to implement. So there's a kind of wiring problem in some of the superconducting and silicon systems or solid state systems. So one interesting question is kind of, well, should you put some of that control electronics inside the fridge? I think the answer is you don't need to do that for the megaquop. And so my view is you should innovate as the last resort. Like, this is hard enough, and if we can kind of get away with solving something using technology we already have, then that's what we should do first. I think longer term, you are likely going to want to put the analog to digital components inside the fridge, because that solves the analog wiring problem. The actual decoding problem, so the kind of QEC stack, it likely doesn't need to be in the fridge, because it's actually a throughput problem rather than a latency problem. So it sounds like it's a latency problem in that you read out your data, you pass it to your decoder, the decoder infers the most likely error and then sends a correction, right? So that's the clock cycle of a logical quantum computer, and you want that to be operating at megahertz. But it turns out that you can just delay the whole thing by, say, 100 nanoseconds. This is actually fine, and you can just keep up. And your quantum computer will finish 100 nanoseconds later, but who cares? So I think there are ways to kind of mitigate this this latency problem and turn it into a throughput problem.
Okay, great. Theo, we asked Yuval about his roadmap. What can you tell the audience what yours look like? You mentioned a few days, but what are the next 3 years for you, or 4 years?
Yeah, I can tell you what we're working on internally and how I'm driving the team. So I told you about Helium-1 16-cat currently being iterated upon to go below threshold. Then we'll move on to this 40-cat qubit device to demonstrate all those building blocks. Again, not a very useful machine in itself. One of those blocks will be to operate it as one very good logical qubit, so typically in the 10 to the minus 6 error rate, which is, I guess, a mega Q up. But then again, it's just a single logical qubit. So ticking all the boxes, and then you'll have to scale. The thing that gets me very optimistic at the moment is the fact that with our latest architecture, we're targeting 100 logical qubit with 10 to the minus 8 error rate, using only 1500 cats. So that's a lot. We're not there yet, obviously. But at the same time, it doesn't require any novel enabling technologies. So for example, IBM is operating 1100 transmons at the moment. So it's somewhat on the same ballpark. And at least in terms of wiring, cryogenics, we can just brute force our way through, just like Steve said. We don't need to do some crazy stuff of having the control electronics within the fridge. So we're targeting end of 2028 for that. But the reason why for us it's really the good target is exactly what Yuval said. It's the fact that at this point, we know that there are algorithms with super polynomial speedups, typically in deep physics, in spin chains, things like that, where you can start outperforming classical supercomputers. And it's not a tautological quantum advantage. You're not using a quantum system to simulate itself, basically. So this would be very useful and very impactful. And from there, well, we'll need to scale and work on several engineering problems that come up. And one of the things that is very exciting is also the fact that as we go deeper in error rates, what we're effectively building are more and more accurate sensors. So we're exposed to also novel engineering challenge and novel physics. One of the roadblocks that was very recently lifted by Google was exactly one of those. And I think the story is very insightful in the ups and downs of how hopeful we are for quantum computing. So so the story goes that when Google did their surface code experiment or repetition code experiment published in Nature last year, well, they realized for some time they had bursts of correlated errors. And this is dramatic for quantum error correction because we assume errors are uncorrelated. It's kind of the Fukushima problem where they had all the pumps in the same room for redundancy. But if there is a correlated error like the room being flooded, it doesn't work anymore. So that problem was attributed to high energy particles, so cosmic rays typically, and that seems like a very tough problem to solve. What am I going to do? Will I have to put my machine on a mountain to protect myself from that? And well, they come up with a clever trick of playing with superconducting gaps to avoid this impact. And they basically lifted this roadblock. But my point is, as we go further in our roadmaps, we might discover new challenges, new physics, and those will require clever engineering to overcome.
Really good story. Maybe you might want to put your computer in a mountain anyway, right? But it's funny, in science fiction, they tend to be on a satellite in space. I don't know why, because there are even more.
That's the worst place you can put a machine.
This is not, yeah, exactly. It's difficult to maintain, right? But apparently it's supposed to be the best place. But anyway. So now, if we, if we try to look forward, which is very hard, because I saw all of you are working very hard, and it seems to me that 27, 28, we'll start to see really commercial advantage, which is quite exciting. Actually, it's now it's very close. Finally, I think. If we look beyond that, let's say beyond 2030 and after that, how do you see the future? Do you have any predictions? Any areas that you think where we need to work after? That should be think about. Maybe Steve, you can start, because thanks to your vantage point again.
Yeah, I think it's such a transformative technology. By the time we get to trillions of quantum operations, we will be able to solve the equations of motion of molecules and how electricity moves across a battery, and there are so many kind of underpinning physical properties that we want to understand. And so I think for me, the nice analogy here is, if you look at the aerospace industry, at the turn of the century, the Wright brothers discovered flight through trial and error. Right? They built a plane, and they jumped off the sand dunes, and then it did or it didn't work, and then a month later they try another idea. But today, the aerospace industry uses computers to design new planes, and they're able to do that because we have the equations of motion, like the Navier-Stokes equations, and we have computers that can solve those equations. And so I think when you look at areas like healthcare or the search for a new catalyst, so the chemicals industry, people are still doing discovery. They're still discovering new drugs, new medicines, and so the opportunity really, I think, for us is to build this technology so that people can start designing new products in these industries. And I think that will be transformational. And I think really that's, for me, is why I want to work on quantum computing and why I think we should be building this.
Oh, we are here for that for sure. Maybe Yuval, again, with your computer in the future, what type of things we could do? When is Shore about to be available on QuEra machines, for example? It could be quite interesting to tell to NIST because they are still waiting to give PQC go ahead. But I think it's going to be soon based on what we just said. But
we're trying to deliver the future slightly earlier than expected. And one of the things that has happened with the Harvard report is that customers came to us and said, we thought this was going to be 5 years away, useful quantum computers. And now, through the work that Alice and Bob been doing and Riverlane and us, the timeline has shrunk. And if you believe our roadmap, for instance, that there will be 100 logical qubits in 2026 for select customers, that's really exciting. You should start preparing for it right now. So I think my personal view is we don't have to think about 10 years into the future because there's so much excitement to do in the next 3 years. Now, of course, every technology has its challenges and things that we would need to do. For instance, at some point, do you need optical connectivity, right? IBM needs it today. Neutral atom computers may need it when they have, I don't know, 30,000 or 50,000 qubits. You need to move to the next one. There are a lot of cats to feed.
I like that one.
And so everyone has their issues, but I think the exciting part, other than the technical excitement, is coming sooner, and that's what gets me up in the morning.
No, but that's, I mean, I can tell from also talking to my clients that's, I mean, last year it was all about AI, and now quantum is back thanks to quantum error correction. It becomes a lot more optimistic about doing useful stuff. So that's definitely, and thanks to everybody. But Theo, what's your view on looking into the future beyond? Again, I know you're working very hard on what you're doing, but do you have a sense of what's after that?
Yes. So what we like to do at Alice and Bob is use Shor algorithm to break to RSA 2048 as a benchmark. It's one of the toughest use cases there. So you need typically about 6,600-ish logical qubits with error rate something like 10 to the minus 12, which is in terms of order of magnitude. And so it's a big problem. Now, in our latest architecture, we estimated that it would take roughly 100,000 cat qubits to run that. And then this is a good kind of benchmark in terms of trying to visualize what are the challenges ahead of us down the road. So I'd see two main challenges that we need to address in the coming years. The first one is how to interconnect, because we need an easy way to scale, to mass product unit cells and scale from there without having to redesign from the ground up each time we increase the size of the machine. So we'll be releasing a paper later this year on a modular architecture, but long story short, it gets much easier once you are at the logical level to interconnect quantum computers, to operate them as one large machine. You'll have trade-off between, just like in classical compute, between distributing over several machines and the speed of your setup, but that's about it. Now, the one that keeps me up at night is rather the second one, the price of the machine. Because at the moment, when we include everything, we're at several thousand, if not tens of thousands of euros per cat qubit. So if you translate that to what it means for a machine with 100,000 cats, well, that's a $1 billion machine.
A lot of cats to feed.
Yeah, and a lot of cash to raise to build it. So that's me trying to simplify my job. And so here we need to dramatically reduce this number, at least tenfold, or to make it more reasonable in terms of value proposition. And so here, plenty of areas, but mostly most of the cost comes from the classical electronics. And so we're really happy that Riverlane is making great progress in simplifying this electronic stack, because we need to slash the price of the control electronics to scale. So 100 logical qubit can brute force our way through several thousands of logical qubit. We need to reduce the cost of the machine.
So I think we almost, we finished. Thank you for you. One of the things I take away is that error correction is sooner than we expected, which is thanks to you guys, because that's good for everybody, I think, in the industry. I like your point, Theo, that we also need now starting about again. We need to thinking about other KPIs, number of hubs, but cost is important, because now that so you know how the buyers work, right? They do ROI calculation. So far R was negative, right? so it was a non-starter. But now that R becomes positive, right? Now we'll look at the I, because of course it will be divided by the I. So I think it's important to start thinking about the cost. And also another thing, obviously, it will be to ramp up manufacturing. Because I think we have a few dozen computers in the world. If you really want to get to the market numbers that we think we could get, we need a lot more, which is a good challenge, I think. So thank you guys for your time.
Thanks a lot.
Thank you.
Thank you.
Yeah.
I don't know if we have time for questions or if it was planned or whatever.
Did you notice that Boston is becoming the error correction capital of the world? I mean, you open an office in Boston. You're Boston Consulting Group. You are in Boston.
Yeah.
Professor Shore is in Boston. Right.
Yeah, there's something about Boston, yeah, for sure. Yeah. I don't know why, but...
Any question?
I'm Leonardo from Entropica Labs. Very quick question. I'm asking for a friend, effectively. Your roadmaps are amazing. It's a really interesting time to see quantum computers. Do you think all of the results will happen in your labs? So will you do all of these things internally? Or do you think there will be room for not just specific research centers to try out these things, so from lattice surgery or for the parallel or just simply discovery of new codes? Do you think you will be opening up part of this so that startups or other companies can play with it?
Absolutely. I mean, the interface that we're planning is, on one hand, a CASM interface, so people can run programs, but they're also a low-level interface, so people can experiment with new error correction codes. We have a bunch of smart people, but there's so many more smart people outside the organization. So by opening it up and inviting people to participate and collaborate with us, I think we'll make progress faster.
Same answer here. Academia has always been at the center of our strategy, and it will keep being. So we'll keep publishing and keep inviting more researchers to work on the platform. There is work for everyone and even way more, so please join.
Olivier has a question, right? And it's going to be tough. It's Olivier, so...
No, it's just for Yuval. What is the overhead of the post-selection in your experiments? Because all the good fidelities you had, for example, with the GHZ state with 4 qubits were due to post-selection. I wonder what's the overhead, I mean, in time, whatever.
I mean, I think the 48 logical qubit experiment was an 832 code, which was error detection. The 2-qubit gate fidelity, I think, was 99.5 on the physical qubits, and on the logical qubits it became better. But I'll have to look.
I saw 7% for the 2-qubit gate in the paper.
I'm not sure. I'll have to look and get back to you.
Okay.
Maybe one last question. Nobody wants to try. You have these experts. Yeah, there's one last question.
My understanding is that some of the errors are very related to the kind of hardware you're running on, right? So what is the role in this of software companies, or in other words, how will the software stack look like? Will companies keep on developing their own software error correction because they know their hardware better than any other?
Yeah, so we've seen that we can improve the performance of the error correction stack by addressing the dominant source of errors, or using kind of more information in the underlying system to kind of inform the decoder. And the kind of intuition behind this is, decoding is basically an inference problem. So given the data, what's the most likely error? So more data is generally better, but that comes at a cost. So there's a balance that I think we're still trying to figure out of I could just chuck more data at this, but now I have to process it, and I have to process it within the next 100 nanoseconds, whatever. I have a very tight budget to solve the problem. And in fact, you see this in other areas. So like our VP of engineering, Marco, he used to work at CERN, so he did the Atlas 1 upgrade. That processor is 46 terabytes per second. That's like Netflix global streaming. But before that happens, it actually chucks out a whole bunch of data. So there's like petaflops per second. And it just completely ignores that data because it's just too much to even look at it. So there's a balance here between kind of how much data you've got, how you can use that effectively in your model, and then how quickly you can solve your model. And so that's really the kind of challenge of implementing error correction. So yeah, I think it's a great question. We definitely see big improvements in using the kind of, or addressing the underlying source of errors. So I don't think it makes sense to say, I certainly wouldn't say Riverlane is agnostic to the qubits. That's a ridiculous kind of concept, I think. But yeah, sharing the knowledge across the ecosystem is quite different.
It's a good segue to the next panel that will be about error correction. We'll have people from QControl, and they will talk a lot more about the stack. So if you want to stay, there will be some more about the error correction stack and stuff like that. But thank you for this great discussion, and we hope that you deliver what you promise. So we trust you, but deliver, please.